Hi, my name is Davey, and today we have something a little different for you. I'm here with Tom, and we're here to introduce you to a tool that you might not be aware of. We're going to talk about how to get the most out of your CNC machine by utilizing the torque chart. Tom, to get us started, can you give me an idea of a broad stroke overview? Where would I use a torque chart in my workflow?
Speaking from experience, I use a torque chart as early on in the programming process as I can, right? The torque chart helps me figure out which tools I want to use, the way that I'm going to set the machine up as far as running a program, the different kinds of tool paths that I can leverage. So understanding how my machine reacts to different scenarios helps me get the most out of it. And that torque chart's one of those tools that I use to provide that guidance.
A torque chart ultimately is a chart of horsepower and torque over time.
Yeah, RPM, right? So it's the horsepower and the torque at different RPM ranges. And then the percentages are going to be also with a time on it, typically, because while you might think, okay, I can run something until it stops, it's actually a little more nuanced than that. If I'm running at 100% on machines like this, it can do that continuously. So 100% spindle load, for instance, it'll just run, right? But at 125%, maybe I can do an hour in the cut, at one time. And all the way up to maybe like 300%, where I'm good for maybe 30 seconds or so.
Oh, sure.
So it lets you look at this chart, and based on how hard you're working, the machine gives you a little bit of guidance around how long you can work that machine at that curve.
I think the burning question that most people have is, if we know where the spindle's going to stall out, can you give us a summary on what is going to happen at that point? If I push it too hard, I'm just running hard in the paint and I get to that point, am I going to damage the machine? Am I going to wreck my part? Am I throwing something? Lay it on me.
So I'm going to speak specifically to the 1500 though right now, because it'll be a little different based on which machine or control or how many different sensors we have on it and things of that nature. I found out the hard way during my cut testing. I actually pushed the machine to 300% spindle load and let it cut until it failed, until it stopped. And it was the most elegant failure I've ever seen.
Oh.
The machine basically went into a fault mode. The spindle stopped, the motion stopped in concert with one another, which is important because it also meant that the tool wasn't damaged, the part wasn't damaged. It basically just said, and I'm done. And the only thing I had to do to recover from it was press the reset button on the screen, which turned all the motors back on. And I jogged in Z away from the part, and I inspected everything to make sure everything was okay. I went back and I reprogrammed and said, okay, let's bring this down to something more reasonable. And I went to 200% and then down to 150%. Actually, I hit 180%, 150%. And I decided for my cut testing, I was going to stick right around, I wanted to say under 125%, because for cut testing, I'm simulating, I got to keep cutting and cutting and cutting until, power turns off, right? And so, but I was able to go ahead and do that and recover quickly and go. Like I said, I was really very pleasantly surprised at how the machine handled a fault.
Sure. Yeah. It sounds like a perfect opportunity to plug a different video we have out that talks about PathPilot and how you can start in the middle of the program if you have to go back to your computer to reprogram something and change one operation. You can recover quite easily, I think, anyway. One of the things you just said kind of brought me to something I wanted to clarify. So I'm looking, I've got the paper torque chart here. What I'm looking at here is this says at 100%, I can run indefinitely. At 125%, I can run for about an hour. At 150%, I've got 4 minutes and 25 seconds. At 175, I get 54 seconds and it tapers off from there. So commanding the spindle is not going to affect the power needed. Spinning a spindle in free air, I guess, is my point.
Oh, right, yeah.
I'm not affecting how much load is on the spindle. So give me a kind of a summary of how I'm going to push the spindle past that 100% mark, and under what scenarios?
Yeah, so basically we've got a couple of things that go into it. And again, this goes back to the how much can I remove and how quickly can I do it and things of that nature. The ways that I was adjusting those different levels that I was running at was by changing how wide of a cut, so the width of cut I was doing. When I was doing a 300% cut, I was using a 3/8 inch cutter, and I was cutting at a 50% width of cut in an adaptive toolpath, which really adaptive is meant between 5% and maybe 20%.
Sure.
So 50% was a lot. So I backed off to 30% and then 25% and then 20%. And each time I did that, I watched the spindle load drop significantly, right? So that's one way you can do it. The other way is managing your depth of cut, right? So, you could go with shallower and shallower cuts, but again, if you're leveraging adaptive toolpaths, you want to use as much of the cutter as you can, right? So I just did it by the width of cut. The other thing you can do is slow it down, right? So it's a direct relationship between the feed rate, the width of cut, and the depth of cut.
Okay. And what helps me understand this, especially when I first got started, was shoveling snow. I could do tiny little scoops and just move my hands as fast as I possibly can, or I could do giant scoops very slowly.
Right.
And if I understand what you're saying, ultimately the sweet spot is somewhere in the middle, so you can have a pretty steady rate of travel while still removing as much material as possible.
Yeah, with that analogy, what you're really trying to achieve is that balance of as much snow as you can move without wearing out. Right? So your stamina of, I can get as much as I can here, so I'm not spending all my time moving as fast as I can and wasting that motion on just a little bit of snow. It's that sweet spot, right, of where it intersects of I'm getting as much snow as I can move without wearing out, and I can do this all day long.
Yeah. So if we have established a sweet spot, one of the things you can see from the chart is kind of where that power per RPM is going to be maximized. So why not just always make sure to be in that sweet spot, or what scenarios would I want to not be in that sweet spot?
Okay, that's a good one. So this is where you start to get into the art of programming, because the science tells you need to be right here, right? But the reality of it is maybe you don't have the right size tool necessary to be spinning at the right RPM to be at that particular range. There's ideal, it's called surface feet per minute, right? And so that's literally, if you think of it like a tire, right? And how much ground the tire is traveling as it's moving, right? It's a direct relationship between the diameter of the tire and the RPM of the tire.
Oh, sure.
Right, and you get into the whole pi r squared and the math. But effectively, that's what you're doing, right? It's the surface foot, and we're using all imperial on this. But so I was just doing test cuts in 304 stainless, right? Industry standard starts out at about 200 surface feet per minute. So depending on the diameter of your tool, it's going to have a certain RPM that achieves 200 surface feet. Well, I found that actually my 1500, because I do all my testing, I have a lab down in North Carolina, and I was doing my testing there, and my 1500 responded better at 300 surface feet. And I suspect all of them will.
Yeah.
So, but yeah, so by changing the diameter, so if we know that we want the RPM to be at a certain spot, and we want the surface footage to be at a certain spot, you pick the appropriate diameter tool for that. But sometimes you just can't do that. Let's say I've got a really long cut. Well, I might need to use a bigger diameter tool for the stiffness, the rigidity of the tool.
Sure.
Right? So there's times where you have to vary. And like I said, this is where you got that art. Some of it's just practical of, I don't have any of those, but I have this size tool. And so this is what we're going to work with.
Oh, sure.
And adjust from there.
Yeah. And one of the, from running our PCNC 440, a pretty decent amount, I figured out that, kind of the smaller tools, small step overs, sail through the material. Yeah. I'm not going to put a, 3/8 cutter in there and full slot aluminum at full depth of cut. with any speed anyway. I'm sure you could do it just at a snail's pace.
Right.
And what I've discovered is to go small step over 60, 70 inches a minute, just railing through the material, and I get much higher material removal rates per time. And so I guess what I'm coming around to is that if what you're saying is true, then there's this kind of a bottom end of this as well. If we can't go to an inch cutter because we're just going to, run out of power at some point.
Right.
We also don't want to go too small because then we need 70, 80,000 RPMs to keep up that surface footage in order to actually remove material.
Exactly. Yeah. So there's each machine. I mean, you have to be real about this with yourself. Each machine has certain capabilities and certain areas, ranges that it's going to work well in. And you just want to just tailor what your tool paths are doing for what your machine does well.
Okay.
Right. And yeah, it's I think the first mistake, especially as we're looking at torque charts, I have my cheat sheet in here too, is that we have to remember that like the 1500, it's a BT30 machine. It's not a Cat 50 machine. So and what we're talking about is the tool holder itself and how big those tool holders are. And if you were to look at the different size tool holders and you look at, okay, well, how strong is that tool holder and how rigid is the machine and everything else, it changes the way you program, right? You talked about full slot versus using adaptive tool paths. Fact of the matter is, a full slot, you have to go slower, feed rate. And since we have a one-to-one relationship for material removal of the speeds and the width and the depth, you can achieve the same material removal rates with smaller cuts, but doing it a ton more quickly, right? So it's just optimizing your tool paths and the tooling for the machine that you have.
Okay. So, and you've kind of circled around this a few times, so I just want to center us on a thought here. So you keep saying kind of what the torque chart tells you, and you've mentioned adaptive tool paths. So if you had to summarize kind of what I'm looking at when I look at this torque chart, and I get, materials are different, setups are different. That's a huge factor is, how are you holding your piece? But what is it, can you, maybe this is a dumb question, but can you distill this down into a few kind of key things to pay attention to?
Yeah. I think you just nailed quite a few of them, right?
Okay.
How well are you holding that material? Is it a dovetailed material that you're holding onto that's super strong? Or, is it in a soft jaw? How much of the material you're holding? Are you, choked up on it and you're holding an inch's worth, or you're holding, 70 thou worth? So that's going to make a big difference, right? In how hard you can push the machine and things like that. The material itself, is it aluminum or brass or Hastelloy, right?
Yeah.
I mean, as we get into more difficult to machine parts, materials, then you have to take a totally different approach. And I think one of the things that I really like at this point is the advent of modern CAM systems. The ability to program your tool paths in a really simple manner makes these more elegant tool paths attainable by everybody, right? It used to be if you're hand coding G code, you were taking those full widths because it was much fewer lines of code that you had to write. Okay. Or you could use a canned operation that said, go in this square, but then drop 50 thou per pass until you get to this, right? And it was 2 lines of code kind of thing. Now we can say, hey, I want the most optimized tool path that we can get that removes this material through here and keeps a constant engagement on the tool at this larger depth of cut. And it's just click, you wait a little bit, and then the machine does all the thinking on all this and processes it, does all the crazy math algorithms in there and spits out the code for you. That's where this really shines, right? The look ahead on the path pilot control, the fact that we can put these gigantic files on there if we want to. We don't have to worry so much about the file size and things like that.
Sure.
And so it can really leverage those modern CAM systems to make the machine dance.
Yeah. So one of the things you mentioned was that when doing cut testing, you stalled the spindle.
Yeah.
We know the spindle stalled. We know that PathPilot goes into reset. What happened? Like what inside the machine, are we talking, your spindle bearings got too hot? Are we talking, what, like specifically what's going on that causes that trigger?
Yeah, so the first thing to note is that we have all these extra sensors and we're tracking how much power is going into the motors and things like that. So there was no damage. There's nothing to worry about as far as that, that goes. So basically what's happening here is we're literally tracking how much power is going into it. So now, especially with the 1500, which represents a huge leap in the technology for us. It's servos at every corner on this one, including the spindle motor, which really gives us a lot more control and feedback and, but mostly information about what's happening. Oh. And so it allows us to monitor what's going on and prevent damage by, like I said, elegantly shutting down before something bad happens. Now, that doesn't mean you can't damage things. Anybody can crash a spindle and damage bearings and things like that. This is not a nanny system that's in here.
Oh, sure.
It's simply, we know that this machine is optimized for certain performance factors, and we put, there's some limits in there of how long it can do those things. Yeah. Even when you look at the torque chart, it tells you how long you can run at certain ones. So like 100%, you can do, it can just go continuously. I found that at 300%, because I was engaged in the cut and then moving back, and I wasn't rapiding back, it was just at the cut speed coming back, it had enough time to cool down a little bit that it ran significantly longer than I expected it to. Based on the chart and the time that it tells me.
So quickly, I'm going to recap what you just said, because what you're talking about is you're making a cut, and let's just say the white paper here is my material. Yeah. And so we're cutting around here, and then we're coming off of the material, and now we're in free space. Spindle's still spinning, but we're cooling down because the load has dropped dramatically, and we're coming back to the cut here. Right. And that's what you just talked about. So
exactly. Yeah. That's a great way of putting it. Now keep in mind, if you're really pushing, you're probably going to tick the box, or in this case, in my subsequent testing, I changed the no engagement feed rate up to like 600 inches a minute. And so that cool down time got real short, and then you're not really getting the benefit of it. But so it extends the amount of time that you can run at those loads, but it doesn't necessarily mean that you can just do it indefinitely, right? And then again, on this one, there's not really a chart that says if you are on for 3 seconds and off for 1 second, or that doesn't exist. Yeah. Just know that it's going to be more than what the chart says, but it's not indefinite. Sure.
So, and that leads me to the next question I had, which was, if I'm running at 200%, 300%, 150, whatever, more than full power on any of our machines, am I affecting the tolerance of the part that I can get out of it, or the capabilities of the machine?
Not the load itself. That's not causing anything like that. There's a lot of other factors that could be affecting that. Keep in mind that the harder you push the tool, carbide's gonna, flex a little bit or things like that. So you might see a little bit of change from that perspective. If I've got a really stubby tool, I'm not gonna see anything. But if I've got a 2-inch long 3/8 cutter, it's gonna flex. Oh, sure. Right? You might need to do a cleanup pass or a finish pass to, clean that up properly and get it to the tolerance. But merely running harder than 100% doesn't mean that you're changing any tolerance there. Yeah.
Sure. So we've spent a bunch of time talking about the 1500, and I assume a lot of people that are going to watch this video are relatively new to machining. So I want to cover some broad stroke stuff as well. Yeah. So we're talking about how hard you can run a tool into material. And now the 1500 has a fantastic load meter right there on the screen, so you can actually adjust your feeds and speeds and kind of use that in preparation of programming, or using it, to adjust your program. How, besides looking at the load meter, can I tell when I'm running too hard or too light in a material?
That is a good question. And it is so easy to get spoiled when we have all these extra meters and lots of systems that give you that feedback. But really what it boils down to is a fundamental that you get with time, with experience on running machines. And that's, just observing in other ways, using your senses to help get you that feedback. I, more often than not, I rely on my ears, what I'm hearing and what I'm seeing, what I'm observing. Sometimes I'm even putting my hand on the machine to feel for vibrations, right? It just kind of depends on what's going on. That being said, if somebody tells you to just listen to the cut, you'll figure it out. That's not helpful, right?
I hear it. It's making noise.
Yeah, but I don't know if it's good or not. Is that a good noise? Is it a bad noise? I don't know, right? So I'll give you a couple of tricks that I listen for. How loud is the cut? Now, this will vary based on the cutter. I mean, there are certain cutters like a shear hog that are just inherently loud, right? But in general, a good cut's not very loud. You'll hear variations in the volume of the cut. But I'm also listening for things like a ringing noise or chatter where you can hear it. It's really, chatter is actually a vibration. So if you're hearing something like that, especially if you're hearing a squealing, which generally is an indication of rubbing, that you're not cutting the material as fast as you could, I generally will speed the feed rate up. Right? I don't want to rub the cutter because it'll basically just burnish the tool and wear it out. Right? It just wears the cutting edge off. So speed it up. Other things might be you're at the wrong RPM range. More often than not, people are like, crank it up, right? But you may not be in the right RPM range for the torque required for that cut. So sometimes it's slowing it down. So what I listen for is, if I'm running, let's say, I'm going to throw a number out there. So 8,500 RPM, and I come into the cut and I hear the RPM range, or I hear the RPM drop. I'm pushing too hard, right? So I hear it drop, it cuts, but then it comes out of the cut and I hear it come back up again because it's not under a load and it's easy to do. Think running on water versus running towards the beach, or you're on the beach running and then you get into the water and it really slows you down, right? Same amount of work, but you're not going as fast. Hey, turn it down a little bit. Turn your speed down so that the RPM range is the same, or adjust your width of cut or your depth of cut, right? Because remember, those are all directly related. So I'm listening for things like that. I'm also looking at the chips that are coming off of it. Am I getting good chips? Are they curling? Depending on the material, I might be looking for the color of the chip. Is the heat coming off in the chip and I'm getting a nice straw color because I'm cutting mild steel? Or is all the heat, because I'm not moving fast enough, the heat's building up in the part or in the cutter itself, right? So these are all things that you get over time, but the big thing is just to pay attention to what's going on.
I'd like to add to your thoughts that one of the things I pay attention to is a change in sound.
Yes.
If you're engaged in the material, it should be a rather linear sound. And, cutting aluminum dry or with, limited coolant, if you start to, gull up that tool, your sound will change. If you're parting off on a lathe and the sound changes, that means you're losing something.
Especially parting on a lathe, right? You're actually going to hear it'll go from a lower tone to a higher tone as you get smaller.
Yeah.
And eventually, so you come to expect this particular sound of this little lip kind of coming off, and then when it's ready to release. Yeah, that's a good point.
Yeah.
What else might we cover on that? I think that's the big one. The change, though, that's a big point, or a really good point, because it might mean that the tool itself is getting dull. If you're using inserted tools, it might mean that you've chipped a tooth on the tool or on the insert, and you might need to rotate your inserts. So always paying attention to the change in sound is important.
Or catastrophic example, if the part shifts and you're now all of a sudden getting too much material.
Yeah, I had this really nice cut going until the part moved and I went from a 5% engagement to a 30% engagement. You're gonna know real fast.
Yeah. Awesome.
Great. Anything else?
I think that about covers the questions I had prepared.
Awesome.
Is there anything that we missed that you want to toss out there for everybody?
No, but I just want to remind everybody that we went through the torque chart information on our blog posts. I think we released it this summer. If you want to get into what this torque chart looks like, how to read it, as far as the actual what the curves mean and things of that nature, things that weren't quite easy to describe in the session today, you can find that on the blog post.
Awesome. Well, thank you, Tom, for your time today. For all of you at home, this is the first time we've done something like this. So if you like the format, if you have anything else you'd like us to cover, drop some comments down below. And feel free to reach out to me, presales@tormach.com. You can find us also on our user forums, forums.tormach.com. Have a great day and go make something.